Okay, so today we'll primarily dive into smart contracts and Solidity programming 101. So the smart contract term is actually not new. It was coined by Nick Szabo in the 90s, and kind of the way he defined it was a set of promises specified in digital form, including protocols within which the parties perform on the other promises. Now, smart contracts, if you think about it, they're first of all not smart, and second, they're really not contracts. Rather, they're immutable computer programs that run deterministically, modifying blockchain state. But of course, everybody uses the term smart contracts. Now, smart contract bugs cost a lot of money. In 2021, it was $2 billion. In 2022, now we're up to $3 billion. And that's despite the bear market that happened. So if we wouldn't have had a bear market, that probably would be $10 billion, if not more. We talked about this previously. I mean, a smart contract essentially takes a transaction as input, plus, of course, the current state as input. It has to be invoked by an EOA or by another smart contract. But if you think about the chain, an EOA needs to be at the beginning. And then what the smart contract does, it essentially creates a new state. And while it's executing, it may emit events and logs. So smart contract properties. Smart contracts are dormant. They need to be invoked by a transaction. They're permissionless. Anybody can deploy a smart contract with no special permissions. They're composable. Like one smart contract can call another smart contract. They are immutable, meaning once deployed, the code of the smart contract cannot be changed. The exception there being the destruct functionality. And then the other exception is really the state of the smart contract could influence the execution of the smart contract. And think about the proxy pattern that I talked about, where essentially you have an interface. It points to a particular implementation, which is controlled by a state variable. You can update that state variable and then effectively change the implementation. And this actually has been a big discussion point. Like I think initially within the blockchain community, everybody was like, it's immutable, code is law, you don't change things. And I think Web3 community has grown up a little bit regards that stance. Smart contracts are deterministics. They produce the same output with the same input. This allows them to be decentralized, such that if Duke, you run a node and run the smart contract with the transaction, and Korea has a node as well, it will produce the same state. And then lastly, they're constrained in that they only operate on the current state of the blockchain. So no real world information is available directly. In order to get real world information, you need to use an oracle. Now, there are a bunch of smart contract management tools that allow you to perform actions like, hey, I want to write to the blockchain every hour. In order for that to happen, you need to have an EOA, an externally owned account, that issues a transaction on chain every hour. And of course, you can do that manually, but there's a whole bunch of tools that allow you to do that and configure it kind of in a secure way. The primary tools are OpenZeppelin's Defender and Chainlink's Keeper. So think of like essentially a blockchain cron job or scheduled task. That's kind of how those tools work. All those services are not decentralized, right? So you now have a decentralized set of smart contracts, right, that are censorship resistant, and the system is reliable, right? Ethereum hasn't gone down for a long time, but these systems are, of course, centralized. And so if they go down and you rely on them, then your protocol would get impacted. Smart contract languages, there's a whole bunch of different types of high-level languages depending on the chain that you're in. You may be surprised to hear that Bitcoin actually does have this concept of smart contract. It's the Bitcoin scripting language, very limited in terms of what it's able to do. Some chains have adopted, out-of-the-box languages like Algorand. You can author smart contracts in Python and Solana and Rust and C, C++. But for other chains, it is a new language. And so Solidity is kind of the main high-level language on Ethereum. And we will talk about Solidity. Now, how do you deploy a smart contract? So we last time talked about write transactions, right? And so we constructed a transaction by looking at the smart contract ABI, right? And then basically invoking a function on a smart contract. And so the to address was the smart contract address, and the data, the input data, basically contained what function to invoke and what the parameters were, right? So that's how you invoke a function on a smart contract. So how do you create a new contract? A new contract is created by sending a transaction to the 0 address. And then the data field contains the contract creation code. It's not just the contract code, it's really the contract creation code. So there is like some memory copying that is happening. And so if you look at a contract creation, so let's just kind of do that real quick. I always want to jump into the block explorer. All right, so let's look at any sort of contract. See, there's a contract. We have the code here. And so one thing to notice here, this code is different than, so here's the contract creation. Now again, the way Etherscan displays this information, I hope this is quick enough, displays this information, it looks like, oh, the from address created this contract. But really what happens, and so the to kind of looks like the contract, but what happens is this EOA sends a transaction to the 0 address. And so this is kind of not shown how it actually works under the hood. And then here is the contract creation code here. So this is the code that we got from the contract. And this is the contract creation code. So it's slightly different. Is this basically now, when you send to the 0 address, you don't know the contract address that gets created. It gets created by the EVM. So in the transaction that you send to create a contract, nowhere in there do you specify the contract address. It actually gets generated deterministically based on the deployer address and their nonce. So it basically takes the deployer address, nonce, and hashes that, and then that's the contract address. And so what that allows you to do is to actually determine all the contract addresses that somebody is able to deploy before they actually do so. This is the way that the standard way that you create a smart contract, and it uses the create opcode that then calculates it based on the address and the nonce. But there's a create to opcode that allows you to specify the contract address. But I haven't covered that in this slide. And that then bears some risks where you could have a contract on chain 1 that holds billions of dollars. And then you could potentially go to chain 2, like a side chain or a rollup, and create the same contract address. And that actually has happened in I think it was the winter mute exploit, where there was a contract deployed on Ethereum mainnet, and then somebody deployed, an attacker deployed a contract on Optimism with the same address, and then somebody thought they were sending it to Ethereum mainnet, a whole bunch of funds, where actually they send it to Optimism, a whole bunch of funds that were essentially
style tactic. Like, hey, I sent you an invoice to this endpoint, it looks right. You know, check the address on Etherscan, and it went to the thing you thought it was going to, and you missed that the chain ID was.
exactly. It's a chain ID that would be different. Yep. One more thing, the smart contracts, they do not have a private key as it executes transactions as opposed to creating them. So how do you create smart contracts? It's in the Solidity programming language. It compiles into EVM compatible bytecode. And so you can create a smart contract with Solidity for all the EVM compatible chains: Optimism, Arbitrum, Avalanche, Phantom, Binance, Polygon, Ethereum. So kind of code once, deploy multiple times. Was created by Gavin Wood in 2014. Gavin Wood is, he was early involved in Ethereum. He is the author of the book that you're all reading. But he left the Ethereum space many years ago and has gone off to develop the Polkadot ecosystem, the Polkadot chain. So that's kind of his brainchild. And then it was developed by the Ethereum project Solidity team led by Christian Reitwiesner. It's statically typed, syntax resembles JavaScript and TypeScript, and it's object-oriented. All right, you can kind of see that if there wouldn't be the window right here. So this is a smart contract. This is essentially kind of ERC20 token-ish. Kind of doesn't adhere to the interface, but it's basically a token from scratch called coin. And so let's kind of go through some of the aspects here. So first of all, up here you see the compiler version. There are some differences within compilers, and so kind of specifying the compiler version is important, so you're not introducing some vulnerabilities where you're kind of relying on a feature in your code that has some issues with the compiler version. Then up here, which you cannot really see, is essentially the state variables of the smart contract. So have you all done object-oriented programming? Okay, so then here are state variables. Say again? Parse, that's right. Then it defines the event here that you can then later emit. One thing to point out here in this language, you have some special types like address. Then there is the constructor here. And this is actually something that changed, I think, with Solidity 0.8. A constructor used to be the name of the class. So you would have had like something like coin, but that then created some vulnerabilities because if you had a typo, then it was essentially a public function that could be invoked. And so they changed it. So now it's a constructor. It just says constructor. Oops, sorry. Then you have special variables. So it's essentially context that makes sense in kind of a block chain context. Like, so for instance, you get like message.sender. It's a special variable, or the current block or the block timestamp. That is all available to you. And then you have functions that then essentially operate on the transaction input or the state. And that's really, there's all to it. So then let's go through some specific aspects. So functions. So the function signature starts with the keyword function and the function name, and then a set of parameters. Then you specify the visibility and the behaviors, and then modifiers, and then a return type. So visibility, there's 4 possible value. You're quite familiar with those: public, external, internal, and private. And what that does is really restrict the who is able to call that particular function. Public can be called externally and internally, external only externally. So any function that is either public or external can be invoked by a user. Internal can only be called internally or from derived contract, so from within the contract that that is running, right? It can call other internal functions, or if you inherit from the contract, you can call it as well. And then private can only be called internally from the same contract. So if you derive it, private functions cannot be called. Does that make sense? And then the behaviors, that I think is probably a little unusual, only really exists in the context of Solidity. It basically tells you about what the contract does with the state. And so a pure function does not read or write state. It basically, think of like an add function that takes 2 parameters, right? It just adds the 2 parameters and returns the sum. Doesn't write any or read any state. A constant is just an alias for view, and view essentially basically tells you that it does not modify state. And so as a result, you can call that function and don't have to pay transaction costs. Nope. Pure has no cost either, because it does not write any state. So there's really only costs involved if you write. And so that is really the case if you don't have any behavior specified. So that's kind of the default. And then payable is a keyword that basically indicates that the transaction can send Ether. So if you create a transaction, you specify the input value, which is essentially the function selector and the parameters, right? Of the function that you want to invoke. But then if you also send Ether along, the receiving function has to have the payable keyword, otherwise it will throw an error and revert. On this slide. So how do you fund a contract? So we just talked about the payable function, right? So if there's a payable function, then you can send Ether to it. But you are deterministically able to calculate future contract addresses. So Colin, if you're deploying a contract tomorrow, and it doesn't have any payable functions, theoretically, it could not ever have Ether, right? But what I can do is I can calculate the contract address before it is deployed and send Ether to the EOA it represents. Does that make sense?
So in that event that I do that, it's like a contracting
Is a smart contract library. All right, well, OpenZeppelin is a security company, and they have smart contract libraries, and I don't know, where is the wizard? Okay, that allow you to basically add things like ownable or roles that then could be used to manage basically access to certain functions. And it is highly recommended generally to use these smart contract libraries because they're already audited, reviewed, they're used extensively.
Just like Log4j.
Just Log4j, yes. And so that's certainly what is recommended there. So the two exceptions with the payable is you can send Ether before the smart contract is created. The other exception is self-destruct. If you run self-destruct, you specify the address to which all the Ether that the contract holds sends to, and it does not, that address could be a contract, and it does not have to be implementing a payable function.
It's just a map.
It's important to remember that you cannot make assumptions around how much Ether a smart contract holds, because there are these conditions where you can just send Ether to the smart contract. Okay, so then a function can also have a modifier. And the way to think about the modifier is essentially, it's kind of like a wrapper around a function. I don't know whether you guys know aspect-oriented programming, kind of is similar to that. And so basically here you have a modifier only owner that basically at the beginning of the function checks that the message sender is the owner. And then this underscore semicolon is essentially the function implementation that gets swapped in if you specify the modifier on that function. Okay, state variables. Type name, visibility, identifier. The visibility, similarly to functions, public, external, internal, and private, maps exactly the same way. But as I mentioned last week, the data is on-chain is not confidential. So these visibility modifier do not do anything regards to confidentiality of the value that these state variables hold. It is really just who is able to access these variables from other smart contracts. So a contract can terminate with an error, and there is a variety of ways to kind of raise an error. So there's the assert, which is essentially evaluates a condition to be true, and if not, stops execution. And so, for instance, as a parameter is getting passed in, you want to maybe assert that it is within a particular range of values that you would expect, right? Require, similar to assert, but used more when there are expectations of a condition. So variable, or actually, I'm sorry, I just kind of messed that up. Require is what I just mentioned, and assert is more of a condition to be true. The require can also include a message that then gets exposed when the error is being raised. And a revert is kind of like a throw exception. So it will stop execution, output an error message. And this also can be used to create better error messages if other functions called simply revert. When an error gets raised, the entire state that was changed so far will be reverted, right? So think of a contract that executes, it modifies variable A, variable B, and then an error gets thrown. All these state modifications that were made by that transaction are thrown away. That's right. Yes.
You have to handle that explicitly, or
happens automatically. Now that creates some very interesting, there's this concept of flash loans. So a flash loan allows you to borrow an insane amount of money, digital assets. You can borrow 1 million Bitcoin. Well, the logic of that flash loan provider, and Aave is one of them, is basically it says, hey, I give you a whole bunch of Bitcoin, but you have to pay me back in the same transaction with interest. And if I fail to do that, then the entire transaction rolls back, right? And you never really borrowed those Bitcoin. So it's a kind of unique loan concept in the blockchain where you can borrow an insane amount of funds within the same transaction, and that becomes this is used legitimately.
It's arbitrage free.
Yes, it's well, not free. You have to still pay the interest.
But like you don't need the base capital to make a large bet.
That's exactly right.
I could make a $1 trillion bet. I'm right. That all works out, and I get to keep the
profit.
The profit of the options.
That's right. If you can do it within one transaction, right? So a lot of the way it works is, right, like assume like 2 decentralized exchanges that have different prices for ETH, right? You can buy it on one cheap and sell it on the other more expensive, and that will adjust the price. Now, I could deploy my own capital to do that, or I can use a flash loan, right? Where I say, hey, I'm going to borrow 1 million USDC, and then I will buy ETH there, sell it there. I then again have USDC back, and I repay that flash loan.
Look at like where different chains are at as far as if it's profitable even this much, and I know how long it'll stay profitable for. Like how big of a loan can you get? How quickly you go? Yeah, that feels weird to not have the control of. Like that seems very open to speculation. Like I mean, there's the cost of the transaction, I guess, to keep me from doing too much speculation, but I feel like you could look for large enough wins, or maybe not.
But like the same wins, so you have to do at the same time, the price will change in real time.
That's right. There's a lot of competition. Yeah. And also you have to think about that your transaction sits potentially temporarily in the mempool. And so others can see what you're about to trade, and then they can copy a transaction, submit it with a higher gas price, and then their transaction get mined and you're not. And so that's where the flash bots come in, where people basically submit directly to the miner. So your transaction is not temporarily in the mempool, and there's less of a risk of front running. But MEV, which is arbitrage, is extremely competitive. I think it's very difficult to make money on Ethereum. But if you look at more obscure chains, probably opportunities there. But then you, of course, have kind of a liquidity problem, but maybe that's actually a good thing because that creates more price discrepancies. Yeah, and you know, if you look on YouTube, ton of tutorials on how to do MEV.
All of them.
That's all right. When a transaction reverts, gas is not refunded, but the record of the transaction still exists on chain. All right.